So we now start the chapter on energetics. This is basically the studying of energy changes in chemical reactions. But before we start that, I want to point out a few things that you should know from earlier, from O levels or physics. In fact, things like the first law of thermodynamics, the law of conservation of energy, terms like work, mc delta T, specific heat capacity. What is the first law of thermodynamics? That energy can never be created or destroyed, but it can be converted to one form and another. So we in chemistry deal with energy changes that go from a certain form of chemical potential energy and heat energy. So that's the kind of energy we deal with. So chemical potential energy is, I should give you that term also. Now you've heard of gravitational potential energy. Gravitational potential energy is the potential energy in relation to or because of the position of a body in reference to the center of the earth. Chemical potential energy is really the energy stored. It's potential because you can't measure it, but it's the energy stored in a molecule, in a chemical, molecule or ionic compound, in a chemical, okay, that can be used to do work. I'll give you an idea. Petrol, methane gas, octane, those have high chemical potential energies. When you burn them, they give out enough heat that helps you drive cars, fly planes, many, and even run electricity in your houses. So we've got that kind of chemical potential energy. That's the potential energy we'll be dealing with. Okay. At this time, you should also know that the unit for any energy or work done is joule. So we'll be dealing in J's and even kilojoules, which represent 1000 joules. Kilojoules. Yeah. And reminder that this formula, which I'm sure everybody's done this in physics in O levels, is mc delta T, which M stands for the mass of the substance being heated, C the specific heat capacity of that substance, and T is the temperature rise. And the temperature rise can be measured in degree centigrade or Kelvin. 1 degree centigrade change is equivalent to 1 Kelvin change. Even though they don't represent the same scale, the change is the same. So, and this is the heat either transferred. So heat transferred to and from a system is the mass into, so the heat gained by a body is the mass of the body into its specific capacity into its temperature rise, or in this case, if it drops, then temperature drops. To give you a context, the specific heat capacity of water is 4.18 joules per gram per Kelvin. Now in chemistry, we tend up using grams because most molar mass are in grams. We deal with smaller quantities, but the SI unit for mass is obviously kg. So you might know specific capacities of water as 4200 joules per kilojoules per kilogram per Kelvin, but this is per gram per Kelvin. So in chemistry, we tend to use gram as the unit. So we got joules, kilojoules, the idea of chemical potential energy, and we'll be dealing with how mostly we'll be dealing with how this is transferred to heat, or heat is transferred to chemical potential energy. And the transfer is similar to what you might think of in terms of potential energy, gravitational potential energy, and kinetic energy. So falling objects, for example, lose their gravitational potential energy but convert that to kinetic energy. Similarly here, chemical potential energy can be converted to heat energy, sound also, kinetic also, or heat energy can be converted to chemical potential energy. And we'll talk about all of those things right now. Now, the second thing I want to highlight is heat transfer. So understand that when we talk about heat and heat transfer, so if your hand touches a hot surface, the reason why it feels hot is because it's transferring heat from that hot surface, which is warmer, to your hand, which is colder. On the other hand, if you touch ice, then the ice feels colder because the heat energy from your hand is transferring to the ice. So when your body gains heat, it feels hot. When it loses heat, it starts feeling cold. All right. And when it's transferring heat to somebody. So when you transfer heat to ice, because height is so cold, through conduction, taking heat from your hand, it feels cold. So understand how heat transfers work. So now if you hold a test tube and it starts feeling hot when a reaction happens, it's because it's transferring heat from itself to your hand. And if a test tube of a reaction feels cold, then it is transferring heat from your hand to that test tube, because I'm going to be talking in terms of chemical reactions. All right. Now, that's the main changes. And also, obviously, we talked about temperature already. Understand one thing, that by definition, temperature, not change in temperature, but temperature of any system represents what? It's a measure of the average kinetic energy of the particle. That's what we refer to as warmth or the temperature. It's a measure of the average kinetic energy of the particles in a system. So the reason why ice has probably 0 degree centigrade or 273 Kelvin is because the average kinetic energy of the molecules of ice is represented by 273 Kelvin. That's a measure of the average energy of the molecules of ice at 0 degree centigrade. Now let's talk about energy changes in chemical reactions. So when a chemical reaction takes place, generally what happens is either chemical potential energy of the reactants, is converted to heat energy, which is generally not only, but we're keeping it simplified to that either a chemical potential energy of reactants is converted to heat energy, or the heat energy from the surroundings is absorbed by the chemicals and converted to chemical potential energy. Now, this is according to the law of conservation of energy. So, energy is converted, not destroyed. So, in some reactions, the potential energy is converted to heat energy for the surroundings, and sometimes the surroundings energy is converted to the chemical potential energy of the reactants. And you probably are already aware of such reaction changes. We call them endothermic reactions and exothermic reactions. But that's something that I'm carrying forward from your IGCSE and O levels. But it's something that we all should be aware of and are aware of. Let me show you some diagrams for that. For example, you have studied the idea of exothermic reactions and endothermic reactions. These terms should not be alien to you in IGCSE and O levels. So what happens in exothermic reactions is that energy is given out as heat. So heat energy is produced. And how do I know something is exothermic? Because if a reaction happens in a test tube, the test tube that you're holding with your hand will start feeling hot. The energy of the reactants is converted to heat energy that you feel hot. On the other hand, endothermic reactions are going to feel cold. They take in heat. It's not like they just transfer heat, they just transfer and then convert it. So you need to understand that energy changes in chemistry are not transferring of heat from one position to the next. It's actually conversion of heat. So, for example, exothermic reactions are those where chemical potential energy, which I'm going to write as CPE, is converted to heat energy. While endothermic reactions are those where heat is converted to chemical potential energy. So there is a loss of heat. This is my way of writing chemical potential energy for now. So in exothermic reactions, the internal energy of the reactants, called chemical potential energy, that you cannot feel, you cannot see, you cannot measure, it gets converted to heat, which is why everything feels hot. The test tube, the surroundings, even the chemicals will feel hot of the reactants. But when you have an endothermic reaction, the whole system feels cold. Why? Because the heat of everything, the system and the surroundings, gets converted to chemical potential energy. So there is a decrease in the decrease in the energy, and then you start absorbing heat from other things, but you get cold. It's like holding ice. Ice is cold, and endothermic reaction is cold. The reason why it feels cold is because they start absorbing heat from your hand, and then that heat is then converted to chemical potential energy of the reactant. That's what's happening in endo and exothermic reactions. Now let me show you in more detail. Okay, I'm going to talk about individually exothermic reactions and endothermic reactions in detail. But one thing before I do that, before I go into details for endothermic and exothermic reactions where I explain the energy changes in more detail, I want to introduce you to another term before we do that. And that term is called enthalpy. And why is that term important? You probably have heard it before. If not, you're going to hear it a lot. Because when we talk about energy changes in chemistry, we actually only talk about enthalpy changes. Because a specific type of energy change is called an enthalpy change. Now, most reactions in chemistry are carried out in open containers, meaning that generally when the reaction takes place, the surroundings pressure does not change. So reactions take place at constant pressure, and the conversion of energy from one form to the other, or transference of energy from one form to the other at constant pressure, is called an enthalpy change. So basically, what's so the word enthalpy change matters, or enthalpy change. It is basically what does the term mean? It means energy changes, transference or changes occurring at constant pressure. That's important. Constant. I need some more space here. Constant pressure. All right. That's what it means to be having an enthalpy change. Energy changes happening at constant pressure. So we will not be using the word energy change as much as enthalpy change. And we use a symbol delta for change and H for enthalpy. You have seen delta H in O levels and IGCSE, and we call that enthalpy change. Any change having occurring at constant pressure. For you guys, just if you can understand that, just take my word for it that energy changes for you guys will be called enthalpy changes. In chemistry, energy changes will only be enthalpy change. So if a reaction produces heat, for example, when you burn methane, methane gives out 890 kilojoules of heat when 1 mole of methane is burnt. So we say the enthalpy change is 890 kilojoules per mole for the reaction. Now, the enthalpy change, you might remember from O levels and IGCSE, also has the sign for endothermic and exothermic reactions. And that's something that you need to know beforehand. So delta H's are, so if delta H, or if a reaction is exothermic, okay, the enthalpy change is delta H is negative. And if delta H is, endothermic, then we write the value of delta H as a positive value. Now this is not because enthalpy is a vector quantity, is because we have denoted these as our symbols to represent, is it energy being converted from one form to the other or the other form to one. So basically, if a reaction is considered to be exothermic, it has delta H will be negative. If a reaction is considered to be endothermic, its delta H is positive. Now we will look into the exothermic and endothermic reactions in more detail right now.